In this video, we are going to have a look how signal travels through your PCB, and it's very important to help you to visualize the fields around the tracks, and then you will better understand sometimes what is happening on your PCB, like crosstalk. So is this what we are going to talk about, Yuri?
Yes, Robert, that's correct. This is everything about crosstalk and how to understand it and where your signal is actually.
So we will start with a very simple example. Two-layer PCB. Two-layer PCB, it means it has track on top layer. Then there is very far away, there is a ground plane or the second plane, which is called reference plane. And this is a very good example because we would like to show how bad the two-layer PCB is. And the main reason is because the reference plane is very far away from the track. Very often for standard PCB, two-layer PCB, it's 63 mils or 1.6 millimeter. In our case, you set up
1 millimeter.
1 millimeter. Okay, so 40 mils. So let's have a look how the fields look when we have the track on top layer and reference or ground plane on the bottom of the PCB.
Right here, we're looking at the values of fields down to minus 60 dB. So, and we can switch to color map. Oh, not this one, but that one, color map. And instead of arrows, now we have colors representing the value of the field, electric field in this case, in dB.
I would like to stop you. So basically, on the graph, I can see the Y is in millimeters. So basically, the field, it goes as far away as like 5 millimeters?
Yes, it's if you get closer to this axis here, we can see that at minus 5, plus 5 millimeter, and the track on top is 2 millimeter wide because of that 50 ohm. You need 50 ohm, and the electric constant here is 4.2.
Oh, this is something what I would like to point out. So in all the examples what we will have today, we will route the tracks by 50 ohms, and the width of the track, it depends how far the reference planes will be. So the width of the track will be changing a little bit between the examples. So for this kind of two-layer PCB, the track has to be 2 millimeters wide, 80 mils, to have actually 50 ohms impedance, correct?
Yeah, it's about 49.69 ohm. Right here, we are visualizing it at 1 gigahertz. Probably didn't compute it at the other frequency. Oh, I computed it as 10 gigahertz. And this is where electric field, let's take a look. And that's going to look different. It's close to where this structure start radiating, essentially. You can see, yeah, electric field. Let me just close
Okay,
this.
so the plus minus 5 millimeters, it was for 1 giga.
Yes, it's for 1 gig. And now it radiates like this.
For 10 gig, it's just...
And you can see electric field over here. It's characterizes the field that propagate in completely different direction from what you want. So it's where the structure very close to high order mode propagation, and it works like antenna essentially on PCBs. This is the main disadvantage, I would say. This high dispersion of the characteristic impedance, change of characteristic impedance with the frequency. Plus, if you get high order harmonic in your signal close to 10 gigahertz or above 10 gigahertz, they're going to radiate and violate all the standards, especially with digital signals where you...
So for standard two-layer PCBs, they can't really be used for higher speed signals. Okay, now let's have a look what will happen when we bring the second layer, the reference plane or the ground plane, where we bring it closer to under the track. What will happen?
Yeah, right here I pre-computed example with 100 micrometer, 0.1 essentially millimeter, much closer.
So that's
And
for mils?
yes, that's about 4 mils, yeah. And you can see that on this scale here, and let's just make it comparison with color view. And we can, just to stabilize it a little, we can take a look at peak value. So again, I switch to side view and I use just S button here. And you can see that right here, the spread is from minus 0.6 millimeter to 0.6 millimeter. So it's essentially 1.2 millimeter spread of the electric field. It's pretty much the same as a power flow. So when we talk about crosstalk, and you can see that in power flow, and the power flows along the structure. So now we look at the energy of the signal propagating along the track, mostly around here. And that's where the main signal, main energy of the signal. But everything beyond this, all those green arrows and closer to and down to blue, this is where you have area where anything that gets into it is going to be coupled.
But I would like to interrupt before we move to the crosstalk. I would like to see same. I would like to see comparison of the first example with the second example, but in same scale. So both can we set both for 1 gigahertz?
Yes.
And then
this is structure at with
this is 1 gigahertz. I can see it. Yeah, it says
1 gigahertz.
Okay, and zoom out until we see 5 millimeters there.
Okay, right here we zoomed in.
Okay,
and
so
right
this
here
is minus 10
out.
up to 10 approximately. And zoom out here from minus 10 up to 10.
Okay, that's yeah. I use minus 5.
More. It must be minus 10 up to 10. So we have it same. Too much.
Yeah, that's it. Minus 10 plus.
Okay.
10. This is a scale.
So basically, this is how it looks. So basically,
yes, that's how it looks. It's now if you now we compare to this one.
Yeah.
And switch this one to peak value as well.
And switch to the other example.
The other example, this one, and I need to select simulation.
So
this
it's
is
like it's like this. So that's what is difference between moving the ground plane closer under the track.
Yes, you got the more space in XY plane, obviously, and if you get we compare crosstalk, we can compare crosstalk at 1W distance at 5W distance, and we will see what the difference.
Let's do this. So one of the advantages why we would like to have, for example, the plane very close under the tracks is because these fields are smaller. That's exactly what we already seen, and based on these fields, we can actually calculate the crosstalk on the other track, which can be routed close to the one which is making these fields. That's exactly what we see here.
Exactly, Robert. We essentially, that's what we see. We put another track in 1W distance. This is that 1W distance. Naturally, this other track...
I would like to stop you. 1W, it means the width of the track.
Width of the track,
yeah.
Right. And the other track becomes kind of conductor in vicinity and gets into the field. And you can see that the fields are getting from up and down to it. And naturally, they, create some currents over there. We can
this
take
is
a look.
which example? The one which is with the thick dielectricum or with the small one?
This is with a small one,
Okay.
thin dielectric.
0.1
This is
or 4 mils.
yeah,
Okay.
0.1, yes. And we can take a look at the magnetic fields, which is also amazing. Magnetic fields, you can see they spread all around. At the logarithmic scale, they do not stop really like electric field. Well, you can see the currents. And naturally, again, they go around this victim trace, and we can take a look at currents there. Oh, let's show the currents on just a second. I'll restrict this area to just traces. And we can see the currents on surface current in this case. Flowing on both sides of the trace. And let me just make more space.
So
here.
basically this field is making the current in the other track. These are the current what we see. They are generated
exactly
with the field.
This field here, electric and magnetic fields, both. Right here we're looking at electric field plus currents, and right here we're looking at magnetic fields plus currents. And notice that magnetic field direction on both ends of the trace. Let me just take a look at the currents. Right here, currents are going in the same, in one direction. You can see right here. And on the other end, they are going in another direction. You can see it. Yeah. And one of the currents is a source of fine crosstalk, and another is near crosstalk. So, but at the same trace, at the same track, currents are flowing in opposite direction and at different ends. And this is the result of the superposition of electric and magnetic field around it. So we can see, and even more, to me at least.
Again, I would like to add one more information for everyone who never seen these simulations. Basically, the signal what we are using, it is a sinus signal. So that's why we see the directions
oscillating.
They keep changing. Yeah.
Yes. Essentially, it's a sinusoidal signal, harmonic solution. And we have, in this case, 1 gigahertz. So it's a period 1000 picoseconds. And we see, electric field, we can see electric field going kind of out and into the conductor. So it corresponds to plus minus voltage.
Yeah.
But power flows always into the same direction. So no matter how electric field or a magnetic field, they oscillating in direction, but the power flows every half of, we can see maximal value, and then it goes to 0, and then it goes again to maximal value. Both half of the period, it gets along the trace. But on the other trace, you can see that the power flow in opposite direction. This is a near crosstalk, and especially below the trace, you can see that it flows in the opposite direction. That's how the crosstalk looks like. So, and power flow density here is energy per second per square meter. Watt in this case, it's joule per second, and that's essentially where energy of your signal. It's not in the tracks, it's in the space, and we can clearly see where it is. So
I would like to highlight this what you just said, because I think everyone who is starting with electronics in elementary school, they teach us currents are flowing through the tracks and voltages and currents, that's what is important. But what we see in this simulation are the fields which are around the tracks, and that's where the energy is traveling, and that's why the environment around the tracks gets affected by the signals, because the signals travels also around the tracks.
That's correct, and that's what really important to understand when, in case of crosstalk. Crosstalk is something that happens in around the tracks, right? In case if you connect two components, if there is a driver, receiver, track, and in addition to tracks, there are always reference conductors, and but the energy is in this space, and everything that in signal space, I call it, and everything that gets into this space becoming coupled.
Yeah.
It's not. It may not become the crosstalk because of some other. There are some other factors that turn it into a crosstalk, but it will be always coupled. Any piece of metal, other signal tracks, any unconnected piece of metal, which when it is coupled, it will become antenna. It may become antenna. So everything that gets into this space, and right here we are looking at simultaneously at electric field and at power flow density on the same graph.
But I would like to point out there are still, of course, there are still some currents flowing also through the track, but usually depends on frequency. They travel more and more outside on the
outside, yes.
Outside.
Yes.
And what was very interesting and what we may also see in other simulations is there can be even higher currents around the edges, I think, but we will talk about this later.
Yes, absolutely, and that's extremely easy to compute in Simbeor. I can show you if we start talking about it. Current density. I select current density. Cut plane along x-axis at 0 and adapt to conductor boundaries. I select this option, and now we will see instantaneous arrows, and it's again current is better to see at logarithmic scale. And now we can see actually current distribution inside the conductors, and let's just switch to linear scale because logarithmic may be a little bit too much.
And here we can very nicely see where the edges are, the currents are.
Yeah, this is and now we're observing this is a aggressor trace, and this is a current and aggressor trace.
Yeah.
So when somebody say, well, currents are flowing, they're actually not flowing. They're going back and forth, and they are not carrying the energy. This is absolutely for sure. The energy carried by those currents that we see is energy that is absorbed by conductors. So that's why it decays exponentially inside, because of it's a process of energy absorption inside the conductor. So if we use like color map, this is 1 gigahertz, and at 1 gigahertz the skin depth is very small comparing to this conductor. It's thickness. And thickness.
That's why it's only. Can we go back to the map, because we could very nicely see it's only really on the outside.
Yeah,
of
it's a skin. It's in the skin.
Yeah, the inside of the track is blue. It means there are no currents flowing inside of the track.
Yes, blue is no current, and this. Let's just try switch back to logarithmic scale and see how it looks like. Yeah, on logarithmic scale it looks like this. So there are some artifacts maybe in color map, but if you switch to arrows, it's a very thin layer in this case, and So, but let's take a look at victim as well. What's going on at victim trace? We look at and that's what's going on at victim. And we can see that in the victim, currents
That's what
are
you say. On
flowing.
one side it goes this way, and on the other one this way.
Exactly. That's what we saw with surface currents. The currents can be depicted as like surface current. I tune something. Oh, and let's switch to logarithmic. And on logarithmic scale, we can clearly see that the currents are in kind of, well, how it can evenly happen in a track that is, let's see how wide it is. It's like 7 mil wide track, but currents are flowing in opposite direction in the victim. And some of them are becoming fine crosstalk and some are becoming neon crosstalk. In this case, neon crosstalk dominates. It's a strip configuration. But fine crosstalk is still visible, and we can compare it quantitatively in form of S parameters. I have those graphs here if you're interested.
So I would like to. So can we compare how big the crosstalk is between this small two-layer PCB and the bigger one, like in numbers?
In numbers, right here, crosstalk was 1W, and right here I have this is on thin substrate. This is fine crosstalk, and it goes. You can see fine crosstalk is, and this is 1 inch segment.
Mm-hmm.
And fine crosstalk grows with the frequency.
Okay, we have to explain again what is on the graph. So
on the graph are S parameters in dB.
dB. So it means basically, ideally, we would like to have no crosstalk. It means very high dB. And if the dB is very low, it means there is a lot of energy transferring to the other track.
Typically on even well designed board, everything is connected to everything. Everything coupled to everything at about -80 or -100 dB. You measure, take two locations, and you'll see the kind of noise flow. But this is not a noise flow; it's an actual coupling. But in case of like -20 dB, if this is fine crosstalk -20 dB, it's around 0.05 volts, 50 millivolts, with 1 volt excitation and 50 ohm termination on both ends.
So if on one track is 1 volt, then on the other one there will be 50 millivolts.
50 millivolts, exactly. So you essentially divide this number by 20 and then take 10 at this power and divide it by 2 because of 50-50 termination. There is also division by 2. It's not 100 millivolt, it's 50 millivolt. So, and then it grows up to -6 or even higher. So it's essentially relatively high crosstalk. And this is on thin substrate. And red curve is a neon crosstalk. And actually on our website, if anybody interested, there is a deconstruction of those crosstalk in my recent tutorial at DesignCon 2025, where we met last time face-to-face. And there is explanation why there are nulls here, why maxima here, why this one grows, and numerical explanation. But right here we can see that neon crosstalk is around -22 dB, so it's a little below 50 millivolts, and it gets like this. But then if you take a thick substrate, well, in thick substrate, again, the tracks are 2 millimeter apart. In case of thin substrates, they are just 0.1 millimeter apart, right? But there it's 2 millimeter apart.
So again,
but the
it's
crosstalk,
80 mils. So maybe we have to also.
yes, 80 mil. We
So-
have to. You can see even my solution has sometime micrometer, sometime millimeter, and sometime mils. I can convert everything to one unit, but then somebody else will not understand this.
Yeah, it's fine. It's fine. So basically,
Okay.
the result of what we are looking at, it means on this, on the standard two-layer PCB with thick dielectric we are kind of getting kind of similar crosstalk, but the distance between tracks
Much larger.
is 2 millimeters or 80 mils, comparing to the example where the reference plane is very close under the track, only 100 micrometers or 4 mils. Then the space between the tracks is how much?
2 millimeters.
No, for the small one.
Thin is 0.1 millimeter.
0.1 millimeter or 4 mils. So
4 mil.
and we are still getting
Yeah.
kind of same crosstalk, but they are much closer. But
And
this crosstalk is
wider
still
tracks.
yeah, this crosstalk is still quite high, no, because there is very
Yeah.
well known kind of rule which is saying it's like 3W or 5W or 1W.
Yeah.
So it means this is telling us what kind of distance between the tracks is safe if they are routed by 50 ohm impedance. So very often, if we have tracks routed by 50 ohm impedance and we would like to be kind of safe, then we should use 5W distance between the tracks, which is 5 times the width of the track.
We can try this one.
Okay,
And,
you have this example, I think. You have
yes, I have this example.
Yeah.
One more note: the bandwidth of this wider of the example with wider tracks is very limited by around about 12, and we saw those electric fields start behaving like strange, right? And power flow actually outside like this, and the crosstalk is growing. With the frequency, and then it in this case you need multimodal computations to predict it, but this is practically unuseful structure above those frequencies. So it's a source of AMI-MC or a source of unpredictable crosstalk or difficult to predict crosstalk. So, but essentially, yeah, we ended up with pretty much the same numbers in crosstalk,
but the tracks are much
larger.
Closer.
Much larger. So structures and 5W.
Oh, okay.
So and
Okay,
we can
first
see this.
Explain what do we see. So this is 5W for what
between
stack
the
up?
tracks. Yes.
Okay.
It's a thin stack up, and you can see that those thickness of traces is about the same in both examples, but right here they look thicker because of the whole scale of it. Let me just switch to.
Oh, I can see
view.
the field even doesn't reach there.
Oh, sorry. I okay, like this. Okay, yeah, you can see that it still reaches a little bit. It's a scale to minus 60 dB in electric field. We can take a look at magnetic field. Magnetic field reaches it for sure, and that's what the right here you can see magnetic field values, and those depicted as arrows. So those are not lines of magnetic field. Those are just values of magnetic field in ampere per meter at different locations here. And then if you take a look at the power flow density, you can see in the air over here, it's still, so the lot of energy is in there. When and this is at 1 gigahertz. So, and that creates the crosstalk. And current density, oh, again, I need, this is the excitation plane, and it shows currents of the cross section of the whole structure. And you can see the currents over here. You can see that there is a fair amount of currents in crosstalk. There is crosstalk.
Oh, you flip the sizes now. Now we are looking. The victim is on the left now. Yeah. Ah, okay.
Yeah.
Okay.
Okay. Sorry, I sometimes I do this, yeah. And this is victim, yeah, and this is this is aggressor,
Yeah.
and this is victim, yeah. And we can see the currents pretty much the same pattern. They are in different moving a different direction or oscillating rather in different direction on the opposite sides of the trace. So how it compares?
Now the numbers. I'm curious.
Numbers. 5W, and we can see. Let's start from thin case. The numbers went considerably down. So instead of minus, and we can compare it right here, instead of minus 20 at about 3 gigahertz, at 3 gigahertz you have minus 42.
40.
So minus 42 is, let's just try to compute it, divided by 20 and 10 at minus. So it's 5 millivolt now, if I'm not mistaken. So yes, 5 millivolt. It was 50 millivolt, now it's 5 millivolt. So considerably down. And then it grows as fine crosstalk grows with frequency. It's again, it's 1-inch structure, and with in the higher frequencies, you have more mismatch between even and odd mode, and then they create this fine crosstalk. Neon crosstalk minus 50 dB. This is level. So and now
and I'd like to explain if if someone doesn't exactly understand the far end and near end crosstalk. Actually, I've done a video, really good video, which can help everyone to understand what is the difference. But basically, when we have crosstalk, it spreads both directions. It spreads also the direction where the signal travels, but there is also crosstalk which spreads the direction from the signal is traveling. So there are two kind of crosstalks.
Yes, well, and if we take a thicker substrate, that's what happened. This is disaster. This is clearly disaster, especially fine crosstalk. And you can see how it becomes unbounded and not behaving as expected from fine crosstalk. It just goes to, everything goes from one trace to another over 1 inch at the frequency about 12 gigahertz. So we create, and this is because of this wider spread fields, and you can see that neon crosstalk on neon crosstalk is actually smaller, this line with circles, and then it becomes larger at high frequency. So same thing. So, but in case of thick substrate, we have 5 millimeter distance between the tracks. So naturally, we start with the lower crosstalk. They are kind of very far. But
Because,
then we end up,
for smaller frequencies, they don't really spread as much as the higher frequencies.
That would be really good to take a look in here. And this is magnetic field. We can see the spread actually, electric field. Oh, right here it's down to minus 80. Let's just switch to minus 60. Yes, spread is not so visible at the scale of minus 60 dB. Magnetic field, same thing, but 10 gigahertz, and this is a power flow density at 1 gigahertz. So that's why the energy of the signal. And then take a look at the.
I'm curious. Oh.
And this is at 10 gigahertz. At 10 gigahertz, and you can see one of the things that really showstopper for use of such structure. And you can see that the energy propagates not only along the track here, but also considerable propagation sideways. Those are leaky waves. And the sideway propagation, that it creates this more and more crosstalk on this track here.
Oh, these
So
are
at high
really good
frequency.
animations.
Yeah, this is unique property of Simbeor solver based on Triops finite elements. So it's based on plane wave expansion of the fields locally, and that allows very kind of realistic and accurate visualization of all types of fields and currents that associated with the propagation of electromagnetic energy.
Okay, when
So
you mention this, so basically this is the software what you designed, correct?
Exactly,
And
exactly.
people can,
software.
if someone is interested, it's not free, but it's not as expensive as some other simulation software. We can go on your website. You can show a little bit.
So on our website, first there is a lot of application notes here and demo videos. On the second part here, there are some videos that we created.
I can see myself.
Yeah, those are links to YouTube. But there are a lot of videos created with this unique visualization capabilities of Simbeor, and there is also so there are prices over here, which is the features that I'm demonstrating. Computation of those features requires Simbeor complete license, so it includes the 3DTF solver, which is not necessary. If you simulate a real board, we use other solvers. So Simbeor has other solvers, which are Simbeor SFS, quasi-static field solver, very accurate for crosstalk evaluation. I can demonstrate it how it looks like on real board.
We can have a look. Yeah, we can have a look by the end of this video on a real board, how actually your software can be used to.
And Simbeor 3DML solver based on method of lines, it doesn't have this nice visualization of fields, but it's still very accurate and usually used as a main engine for the analysis. 3DTF solver that we are looking here requires a lot of computational resources. So unfortunately, this realism of the field view comes with this price of you need and actually computational power of computers recent advance. It made it possible to do it like this and do all those computations. And
but I would like to point out, once all the computations are done, then basically what will happen is what everyone can see now. You can just go through all the kind of views and everything, and you don't need to calculate it again. You just basically use the data which were calculated before. And
yes, exactly as we generated view of the currents inside the tracks, and you can do it on the fly with pre-computed data.
And I think you mentioned basically your free version actually enables to watch these data of these examples. What, for example, even maybe what we are using right now. So
that's Simbeor viewer license. Allows loading existing solution with field views. And there are examples that I use for DesignCon and that we'll use today. They are located in this folder, so you can get here and download some examples, use viewer license, like crosstalk and strip lines, power flow density and transmission lines, and crosstalk and microstrip line. So you can download it and use viewer license to generate different views as you, if you want to learn how
signals travels
how interconnects work basically.
But the viewer license is free, correct?
And the viewer license is free.
Okay.
Да. Yes, you download it, Simbeor, and you select viewer license over just now one help, and there is a viewer license always in here, and that allows to view the fields and compute new fields for a pre-computed problem.
Okay.
And almost all, at least 80% of examples from the recent tutorials, they are available on this Google Drive, and as well as the slides from the tutorial on Crosstalk. It was a very intense tutorial.
We will cover some of the examples. I hope we will have
I
time.
put too many examples.
Time is flying now.
Yes.
There are a few more examples what we would like to show. So first, what I was very curious to know is difference between, routing on top and bottom layer, or having the tracks on top and bottom layer, comparing if they are inside of PCB. So we have two more examples, two more basic examples. Basically, when the track is routed symmetrically between two ground planes, or when it is asymmetrically. So what is the difference?
That's correct. And to illustrate this, I created example with 100 micrometer or 0.1 millimeter or 4 mil, about 4 mil, both dielectric layers like this. And that's the signal space. We're looking at electric field, magnetic field, and power flow in this case.
This is very cool because you can see the signals, they don't spread like everywhere. They just kind of stay inside of the board.
Yes, they are. In case of symmetric, it's much more localized. The localization property of the signal is much better. And so you right here down to minus 60 dB, you don't see anything around, let's say, right here it's mils, and we can switch to millimeters. So right here it's in millimeters, it's like this.
It's like
0.5,
this, 1 centimeter.
0.5 on this side.
Yeah, 1 centimeter in total, like this. Yeah.
Yes, 1 millimeter, actually.
1 millimeter. Oh yeah, 1 millimeter in total. Oh,
yes,
that's like
it's 1
this.
millimeter. Yes, it's you cannot measure it. But now, if you take a look at and compare it with this one, and also put it in millimeters, right? Okay, side and fields. So it's a little bit more spread. You can see that right here we have 1.4, about 1.5 millimeter across. Pretty much the same, minus 60 dB in electric field.
And this is 100 from the bottom plane, and then
300 from the top.
From the top.
Yes,
okay.
yes. So, and again, we can take a look at magnetic field. Magnetic field, you can see it goes a little bit further, but the reason is we can see it further here because of it normalized to electric field has singularity at the edges, and that basically creates larger electric field at the edge. But in magnetic field, it's less visible, and we normalize it to a smaller value, and then we see further here. And the actual value, the actual measure of where the signal is the power flow density. And right here we can switch to color map.
can we use same scale in both cases? I'm just curious. So this is like
Exactly.
0.9 minus 0.9,
Yes.
or do it one to one. Zoom
One
out
to
a little
one,
bit.
yeah.
Okay,
1 millimeter
Yeah.
minus plus 1 millimeter,
Okay, and this one.
and right here we put minus like this, and also switch to color map. Yeah,
Go back again. I'm just curious.
and go back. Right here, spread is more visible, right? And the reason is because of this. There is a remote plane, and remote plane has, in this case, about 1/4 only of currents comparing to this plane, but they're still there, so it's still.
And I think you mentioned there is advantage when it is in the middle. You mentioned something about canceling some of the crosstalks, or am I wrong?
Yes, there are two types of crosstalk again, near and far end. And in case of, let's take a look at, again, one track distance and electric and magnetic fields. And now we can see that they are kind of electric field comes from top and bottom. This is a case of symmetric, obviously. And we're looking at electric field, at magnetic field. Magnetic field, you can see it again goes in both direction, in opposite direction on both ends. As a result, we have currents that again, I remove the currents on. We can see the currents flowing. Let's find a better view. Current going this way and this way. And
now you can see actually half of the current goes this way and half this way.
Exactly. So symmetrically. So a fine crosstalk is pretty much cancelled in this case, but in case of asymmetric stack up, we can see. Let's see, magnetic field. Magnetic field now is not symmetrical around. You can see this. And essentially this proximity, like some people call it proximity, but this is basically current distribution, all about current distribution. It creates this more fine crosstalk. So
because there is more of magnetic field, for example, on the bottom and a little bit less on the top.
Exactly, you can see more currents on the bottom side and less. You see zero currents over here, but right here currents flowing.
This is so cool.
Yeah, that it is. Yeah, and they're flowing. You see, we can take a look at closer look at this. Just computing current density adapt to conductors and take a look at instantaneous values here. You can see again, this is, and I will adjust a little bit, not here, transparency of conductors to make it more visible. And you can see that, and this is currents in the victim. And so they, in case of symmetric, they are symmetrical, but right here we can see
it's bigger on one side.
Yeah, and we can actually enhance them like this to see more, not on the logarithmic scale, but rather on just linear scale. And you can see that this is the current and the victim. So yeah, let's just switch back
this is interesting because I never really thought about impact of this kind of not placing the track symmetrically between reference planes. I was like, I don't know.
We can compare the numbers now. What actual the crosstalk, fine crosstalk, and near crosstalk in those cases, and I got put it on the graph crosstalk with 1W, and this is symmetric case, and magically we have -20.
Wow.
Again, 50 mil neon crosstalk. And this is symmetric stack up and 1W distance between the tracks. And
but the
the
blue
fine
one is very
crosstalk,
low.
yeah, it's very low. Yeah, it can be even lower. We'll see that with 5W it's almost non-existent, but right here we put them very close and do not have fine crosstalk. The odd and even mode along the structure propagates with about the same speed, and they cancel fine crosstalk. But neon crosstalk exists. It's like this. And then if we put unsymmetrical here, neon crosstalk is exactly the same. But fine crosstalk, you can see, it grows from -60 to -35.
Huh? Okay,
So,
and you say you have also 5W, or yeah, 5W.
Yes, 5W. Yeah, exactly. Let's just jump into numbers immediately. And this is 5W for symmetric.
This is so much better. -70. Wow.
-70, and this one -90. -90, -80. And remember, everything on the board is coupled to everything that's about -80 dB. So even on well-designed board. So right here we have with 5W we really kind of pass all the compliance conditions for this. But what about the, yeah, and that's what we have in case of unsymmetrical. Unsymmetrical, we have, okay, this one is symmetrical, and this is unsymmetrical. It's still low. It's still low with circles. This, but it's 10 dB up in neon crosstalk, as well as considerably up with fine crosstalk, -84, -70, 15 dB up in fine crosstalk. This is one of the disadvantages of having unsymmetrical planes like this. There are other disadvantages. So you put planes farther apart, and this creates a space, wide space, that if you want to cross it with vehicles, for instance, that where the radiation from vehicle may take place. So it's very difficult to localize. So the closer the planes, the easier to localize signal in vehicles. And right here, if you take a look at the fields at 5W, we don't see much. Well, at this levels where it's -50, -60, -70, it's very difficult to visualize. So you have to go to very low numbers in here. It's still doable. So if we put a couple of zeros here on electric field, we'll see electric field essentially how it happens.
Yeah, but we don't want to use different scales between different examples, because then it can be misleading.
Right here we're using -100 dB scale to see the crosstalk at the level of -60, -70 dB. So, but that's a beauty of numerical experiment, actually. So you don't have to go and buy much more sensitive equipment. You just well, add a couple of zeros, and here we go.
Can we go back and see the graph? And is it possible to switch on there also the previous examples?
Yeah, we can compare it with the previous example like this. This is our previous example. And right here, we can simply drag and drop this 5W case here. Just not this one, 5W, this one. And it's 1, 2, and 1, 4. And this is where we are with new case.
So this is the difference between routing tracks on top and bottom and routing tracks inside of PCB.
Oh, no, no, we don't compare those. We can switch. They are in different solution, unfortunately. So let's just switch to this one, 5W, Crosstalk 5W. This is comparison of microstrip example of thick and thin and between each other, and we can see that the numbers for crosstalk are especially for fine crosstalk, and fine crosstalk is a showstopper for all microstrip, especially if you want to route something microstrip and RF structure with very small values for crosstalk. Sometimes it's minus 70, minus 80 dB. It's practically impossible. So, and that's what you see in fine crosstalk here. But if you switch to this one, and let me just uncheck this one. So, and 5W again. You can see that we even with
it was comparison between 1W and 5W, the one which you, okay, I understand now.
Yeah, I try to compare 1 and 5, which is obviously 1 is worse and 5 is better. But right here we essentially even at the level minus 60 in both cases, symmetric, unsymmetric. So unsymmetric has a little larger crosstalk, minus 60, and right here mean crosstalk at 5W is around 50, so it's already 10 dB higher. But then fine crosstalk is a problem, is actually actual problem. So it's very difficult to kill it completely, and there is no strategy that reduces it other than shielding. So you shield it, you convert it into some kind of strip line with air and other dielectric. So, but that's again, that's how, if you see something microwave on the board, it usually shielded like a small piece of metal shield. They put it on the top.
So what is a kind of acceptable crosstalk for standard signals? What level?
Well, it depends. If you take a look at specifications created 15 years ago, like Ethernet specifications for 10G, you'll see very low numbers like minus 70 dB, minus 80 dB, which was really doable. Now those requirements are revised because of crosstalk is back, because of you need more tracks, higher density, and minus 40 dB is it depends on the attenuation, expected attenuation of the signal. So if signal attenuation you expect at minus 40 dB, then crosstalk requirements may go up to minus 70 dB. But if you expect only like minus 20 dB, in this case, minus 40 dB, minus 30 dB, it's all depend. And some advanced signaling standards like Ethernet, OEF, chiplets interconnects, for instance, they have compliance metrics for crosstalk. And so essentially you basically in Simbeor you load those compliance metrics, and there are presets for such standards, and then you compare it. And I can show you how it can be done on a real board if you have 5 minutes.
If we have time, yeah, we can do that. So basically, we can say like for kind of standard PCBs, minus 40 can be kind of okay.
It depends. Well, I use this Eric Bogatin's kind of thing. It depends, and it depends on what.
I will show you something. Yeah.
Oh, okay. Yeah, exactly. I wish I had the same. Okay. but it depends on the context of where you do the evaluation of crosstalk, and that's was my part on quantification in crosstalk tutorial. Quantification part it essentially explains different ways to look at the crosstalk. It starts with simple S parameters, or then power sum crosstalk. It's essentially sum of all crosstalk, sum of squares of all S parameters relevant to crosstalk. Some standards put compliance metrics on those. Then it goes on to
we don't need to go to details. I just wanted to give people an idea what is it. There is another example what I would like to show people, and what I really liked is the crosstalk where we can actually see the waves and how it spreads. Because until now we only look at the fields, but we can actually see how the signal travels through the tracks.
Yes, exactly.
Can we show
this is example from my actually tutorial, and I use it in some demo videos and so on. But that's how it looks like. And let's just explain this. Again, it's 1W symmetric strip line stack up. 1W distance between tracks. Tracks are 50 ohm. And this is a static view of peak values of I switch to instantaneous views here and zoom into this area over here. And now we can see right here, it's a power flow density.
So we can now see basically the waves.
The waves, exactly. This is correspond to half of wavelengths. This from minima to minima. And aggressor line is straight. And we can see the victim is getting the crosstalk. And there is some, you can see this power flow along the victim line. It's, let's just uncheck some of those. This one.
This is so cool. This is really so cool. I really hope this will help many people to visualize actually what is really happening around the tracks.
Exactly. So we basically this trace violated the signal space, so to say, and the consequence is near crosstalk and fine crosstalk. So crosstalk on the end that is close to the source of the aggressor signal, and this is other end.
That's what I mentioned before, that the crosstalk travels both directions.
And this it's difficult to trace exactly how. Well, it's a superposition of waves. I always look at this as a superposition of waves in this segment, and then how superposition. The result, we see the result in form of fine in theory, the signal along those two coupled traces, it propagates not as signal just along one trace, but as a superposition of four dominant waves. In this case, it's even an odd mode, traveling in this direction and traveling in this direction. So it's they kind of and this superposition gives us near and fine crosstalk. And that's why you see on frequency domains this behavior where you have maximum, minimum. It's kind of at half wavelengths, quarter wavelengths, and so on. That's the result of this superposition.
So this is 16 gigahertz signal, yeah? Can we have a look on something a little bit faster? I'm curious how the waves will change.
Yeah, 28 gigahertz.
Oh, we can see now the waves are smaller.
Yeah, we can see the spatial distribution shrink basically 2 times. And then we see more fields, and this is power flow density in dB, kind of getting somewhere right here. And those are leaky waves, actually. Those waves that create crosstalk even at relatively far distances. So even with this strip line configuration, you are not safe. At high and higher frequencies, you'll have this energy propagating everywhere if you don't take some measures. And we can discuss what measures.
Yeah, okay.
For
so
instance,
let's have a look. So well, I guess there are few ideas what people may come up with how to prevent this.
yes,
One of them is
yes.
place it further, and the other one, what very often we can see, is placing ground trays between these two tracks.
Okay, I pre-computed those cases, and if you put them further apart, like this.
Yeah, okay.
Okay, fields.
Oh,
Well,
this is cool. You can nicely see the fields. They are not as big
yeah,
as the space between them is, so they are not kind of touching.
in nothing in those sense at the level of minus 40. So let's take a look at 28 gigahertz. But at 28 gigahertz, you can see that it starts gaining fine crosstalk from those leaky waves.
Mm-hmm.
And that spot, it's difficult now. If you even move it further apart, you'll still get it.
Do you know what I'm
It's
thinking
gonna be
about?
lower, but not. It's as stubborn as in microstrip case. You move those apart, and you still have it.
You know what I'm thinking about now? What if there are two signals running in both of them, and for example, in one case they are traveling together, or on the other case they are traveling opposite of each other? What has to be happening with the fields?
Well, let's compute it. What field do you want to compute?
No. We don't need to compute this because we still have other examples. But maybe we can do this in next video. Can you run
Okay.
signals in both traces?
Yes, absolutely.
Really?
Yes. Right now we excite port 1 and port 4 at let's say 28 gigahertz.
Oh, okay.
And compute power flow,
Okay.
volumeric.
Okay.
And see logarithmic scale. Put a little bit of zeros here, and instantaneous.
I didn't know you can do this.
Yes, and this is we can take it cross sections and so on, but you can see this energy that is not now associated with the signal. This signal travels this way. Yeah,
This is really messy.
it's really messy, and I put it down to minus 50 dB. And that's how messy it's gonna be on real board on strip line configuration if you don't get something done about it. And we'll take a look at what can be done about it to basically reduce it and see, and we will take a look at the signal propagating in both directions. So they are both getting some amount of crosstalk here. So this one gets crosstalk here, but right here it's a fine crosstalk in this case will not matter because of receiver is here. So, and from this signal, you're not getting fine crosstalk on this end. So getting signals like this, it's safe in here from the point of view of fine crosstalk. But you still have energy kind of going sideways everywhere, and that's
And if you put them same direction, so it's going to be worse or what?
Let's put them in the same direction. And now I will excite port 3. And we are computing it at 28 gigahertz, which is roughly 56 gigabit per second.
Oh, this looks more messy. Or am I wrong?
I'm sorry?
Am I wrong? It looks more messy, no?
No, it's the same mess. Only in first case it was right here we have more order, and obviously if receivers are on this end, then you have the problem. And if you have requirements below crosstalk below minus 50 dB, you definitely have a problem. But this case is, you can see they are not compensating, they are just propagating in different directions and canceling each other, but then appearing again. Energy doesn't cancel, it's just, it's phase. So, and right here we can see they moving in the energy in the same direction with the same leaky waves and getting the crosstalk on this end, both cases. And right here we have absorbing boundary condition, and you can see the waves that go in sideways, they are absorbed by boundaries.
Okay, so we have another example. So I think you had examples about placing grounded track.
Exactly. What if we put some guard track like this? Yeah. And in some books you can see recommendations on putting it like this. And the only thing that definitely in there is to ground those tracks between the traces. You can see that, the energy now, this guard trace in the middle, and the energy in this middle grounded trace is a little bit oscillating, and we can still see fine near and fine crosstalk here. This is at 16 gigahertz. Let's take a look at 28.
Oh,
at 28,
it just goes
it's a
through.
disaster. Exactly. It just the whole thing will start working as a resonator in between. So essentially, you put few such resonator, and you can create Yagi antenna maybe. I don't know. They will start resonating one by one, radiate energy, and
basically,
but in this case, it's it transmits energy from here through to this victim trace. And
basically, the problem is because we only have two vias, correct?
Only, yes, exactly. And in this case, distance between two vias is not sufficient. It's not sufficient on 60 gigahertz, and clearly not sufficient or visually not sufficient at 28 gigahertz. So the other extreme is just to put just vias in there. Mm-hmm. So like, okay, what if we just stitch the reference points, mm-hmm. top and bottom?
No track.
No track. In between, just stitching vias. In this case, you can see that energy gets actually freely between those stitching vias, mm-hmm. and get coupled to this track here. It's mm-hmm. a beta coupler, so-called. And again, if we increase the frequency, we can see how well this coupler works. Mm-hmm. And this is fine coupler. So that's how we create this, make a lot of small holes between two wave guiding structures, and then the energy gets into, mm-hmm. So let's combine both.
So basically, in this case, we could think like vias, with vias we are creating some kind of wall or something, but it doesn't work so well.
No. It's not. It's the energy. We can take a look. Basically it doesn't shield one structure from another. So the only thing that shielded, and I call it future, and that's I have actually guard vias like this. You can this is you can do it like this.
Mm-hmm. So there is now they are all connected with track.
Yes, they're all connected. There is a track in the middle, mm-hmm. and vias are connecting the traces, mm-hmm. like this. And we see that the level of minus mm-hmm. 50 dB here, I put minus 50 intentionally, no crosstalk at 16 gigahertz. Mm-hmm. At 28, we will probably get some. No, it's minus 40. Let's just recalibrate it to minus 50. Again, put one more zero. Mm-hmm. And it's still nothing. Mm-hmm. So this thing actually works. Well, if you go to extreme, and I bet all boards are going to look like this pretty soon. I mean, this conquest of 448 gigabit per second that we saw at DesignCon, it will require the boards that will look like this.
So ground traces on both sides and
exactly
many,
everything,
vias.
essentially coplanar structure, coplanar routing with a lot of stitching
It's
views.
like waveguide.
Exactly. Yes, it's a waveguide. Yeah, there is actually a type of waveguide that something in between substrate integrated waveguide and strip lines that for potential use for 448 gigabit per second, where you intentionally create substrate integrated waveguide, put a trace, white trace coplanar, white coplanar trace inside, and it creates a hybrid of waveguiding TM10 and coplanar mode, which can be used to transmit signals up to 200 or 300 gigahertz. So without much dispersion. But right here, we don't use waveguiding part of mode. We use just coplanar part of mode. And now let's just go to 28. And right here it's minus 50 already, nothing. And now if we repeat our experiment and put the
two of them
flow,
I'm curious.
Yeah, like on this port, or
okay.
let's which one do you want? This one?
Three,
one?
because that was the worst
3.
one.
Okay. Yes, it looks worse. Yes, and volume, power flow 16 and 28 gigahertz. Okay. And we switch to instantaneous logarithmic scale and put more zeros here. You see how nice it looks like? Content, it's localized. The energy is localized.
I like it. So let's do the real board example, because we still have a couple of minutes. So
yeah,
let's show everyone how your software can be used on real boards, not only learn about how signals travel through a simple track, but how to use it in a real board.
So I create a new solution and pick up this board called IMX6. Let me see. IMX6 Rex, this one.
So this is Allegro file, yeah?
Yeah, this is Allegro file.
Do you have support for Altium too, or then it's ODB++?
Oh yeah, absolutely. You can import it from Altium ODB++, and KiCad actually now support ODB++. We have customers with KiCad. They used to use hyperlinks output format, but now they start using this ODB. So ODB++ is away from Altium or from
ODB++ is kind of standard from all of them. Okay, so we need to explain a little bit what we have on the board. So there is processor. U1 is the processor you can show with the cursor.
This one.
Yeah, there is the processor, and then on the right there are four
DDR
memories,
chips.
I think, actually. 2 from the top, 2 from the bottom.
Oh, from the bottom, yeah.
Okay.
So I'm not familiar with this board, so I actually, when I saw your video and I tried how it works in Simbeor, so and I I'll try to repeat something from. For instance, if
is it bad?
What bad?
I mean the results.
No, everything is perfect. I mean, as is. So there are nothing perfect. Okay.
Do you need to put there some information about stack up or something?
The stack up was imported.
Oh, with the board file. Oh, cool.
Exactly. It may not be exactly what it is. So, for instance, right here, it generated few error messages here, warnings, and no, it was exactly as it was specified in the board file.
Okay,
you can
cool.
see it right here, the whole stack up with all those numbers. It looks like not decay is 4.6. Which is a little bit high. So this is a 3D view of the board generated instantly in Simbeor. And this is one of the technologies that we put some efforts in. And the reason is we wanted to visualize the results in 3D. It's a much more space. So I selected
just up
one,
to 7. You can just up to 7 go.
Up to 7, yes.
Yeah.
One bank of this. And the first type of analysis is electrical rule checking. I click run, and right here I don't see the tracks are a little bit red, which is high impedance. You can see everything. Vias are green, so they are well constructed, and there is a potential crosstalk from those this gray areas. And for the crosstalk, if you're talking about crosstalk, let's just put 4 millivolt threshold for evaluation.
That's the second. I think that's the second bank, but it's routed a little bit further. You can even see it. These tracks are a little bit further than the other tracks.
Yeah. So, and we put some larger distance for crosstalk here to basically improve the accuracy of analysis. Let's just put 5 mil. Okay, and click run, and we'll see the crosstalk. And yeah, there is a crosstalk over here, and you can see the values, and we can adjust to see just the crosstalk. Let me just view. Display control, visibility.
But the values are not very high. Oh, there is like 9.
Well, they look like not very high because of they evaluated locally. So basically, they show you right here there is a 28 millivolt.
Oh, yeah,
and,
28. I see.
Yeah, and potential crosstalk between those parallel tracks over here. And but to evaluate actual crosstalk from simulation, right here, quasi-static field solver was used to evaluate for every cross section, every parallel section found on the structure. But in reality, you need from end-to-end crosstalk. And for this purpose, I will use fast analysis. And again, I use SI compliance analyzer here, switch to fast SI analysis. And in fast analysis, I add crosstalk from scattering parameters, magnitudes of crosstalk as parameters, and crosstalk from pulse response. And pulse response, simple mask, like 10 millivolts. Let's report everything that above 10 millivolts. And we are doing it in real time without any preparation, without pre-computations here. So Simbeor builds the model right here and runs the analysis. And we can see all those red boxes here. Crosstalk. So we can see crosstalk 43 millivolt, for instance, on this structure. If we, well, we can actually get the right here. We can browse just what the crosstalk looks like.
Because otherwise I would have to do it manually for every track or something, or the longest one, or with the one with the longest parallel routing.
Exactly. And we can create a report, actually, collect all the failed, collect And we can see that the value of crosstalk right here. So you can see what is the severe violation is. So it's about 30 millivolts. So if you take a look at all of them, so that's all violated crosstalk on this board. If you put a compliance metric in form of pulse crosstalk. So, and this is S parameters of crosstalk. So there are some, for instance, this aggressor, you can see it's about minus 20. It's probably the closest trace to this particular link.
I have a question. So, if let's say someone is interested to buy your software, how they can learn how to use it?
Well, learning is from demo videos, and most of those demo videos are actually training videos where I do everything from start to finish, exactly like we did here. I imported board, selected nets, ran the analysis, created compliance conditions, and there are compliance conditions for some high speed standards that are coming with Simbeor. So they already have some masks, eye masks, or mask for S parameters for insertion loss, for return loss, and so on. So right here we see this is insertion loss, very clean. Return losses also relatively clean. Short tracks, impedance is close to 55 ohm. So everything is perfect, but crosstalk here is on TDR we can see the tracks actually 53 ohm. So a lot of measurements, and a lot of measurements exactly at the location where they are taken. Those IOs shown here. So learning is really easy, especially this post layout analysis. We turned it into complete automatic mode that does not require some attachment of. There are a lot of things that you can further learn in going into now our knowledge base and like compliance analyzer, and what is compliance analyzer and how to use it, and then you can further kind of get
so this is kind of help.
Exactly, instructions on everything, how to import from ODB, for instance, and you get everything how to import from ODB. It's still it's not AI, but still it's not artificial intellect, but still in there.
I really admire you to creating these simulations and then also create all the supporting materials and everything. Wow. Is it only
Robert,
you creating
give it a try.
Is it only you creating this?
I'm sorry?
Is it only you creating this?
No, we have developers in the company as well.
Okay.
So that's
because that's a lot of work.
It is. We have very advanced team of developers, and that's what we created. Essentially, this project was with this completely automatic post layout analysis started around 2021 during the pandemic. We decided to do something radically different for PCB developers, essentially. Simbeor was kind of research and development project where we tried different methods, solvers, and so on. And then we decided to turn it into, it's based on decompositional analysis. So right here I use fast analysis, but if you want to simulate it in 3D with very high accuracy up to 100 gigahertz, 120, not just those links, but links in general, in high speed links, for instance. So that and take into account, for instance, coupling between vias, just few clicks, build new 3D analysis and automatic. And again, now it will build, it builds split all structure into transmission line sections with coupling, obviously, and accounts with 3D electromagnetic analysis of coupling between those closed views. So if you extract it, I'll show you how it looks like. Again, I was able to hit run button, and it will take few minutes probably to finish this example. But then you'll see geometries extracted for electromagnetic analysis, automatic again. So that's the level of and PCB developers, they do not need to worry about the ports, how touch the ports. And, the only thing they need is just click button, run. That's it. I probably hit the button run. It's running actually. So it's running on my distributed computing on my desktop next room. So you can see it start working on one discontinuity at a time. In a few minutes, it will finish it with the coupling included in those. It's a decompositional electromagnetic analysis called technology.
Mm-hmm. And I would like to say, we didn't talk today about vias, but actually in your software you can do also very nice simulations of vias. We already created a video on this topic, so if someone is interested, I will put the link somewhere. So because it's super interesting, and many people ask like, how do I don't know, calculate impedance of vias, and it's very interesting to see how the fields are traveling through vias. And how the stitching vias are helping to actually guide the signal. Okay.
Yeah.
Are we going to wait, or it's finished, the simulation?
Oh, it may take a few minutes. I don't know how long it will take because of the discontinuities here. Well, it still it went through only 2 discontinuities and still way to go. So
no, we don't. So we don't need to wait. I think
I will just stop it, and I will not stop it. I will keep it. It's a good test. I didn't try it before. Just did it. Yeah.
Okay. I would like to thank you so much, Yuriy. This was very, very cool, and I learned a lot, and it really helped me to visualize a little bit more about how these fields are traveling around the track. So thank you, Yuriy.
Thank you, Robert, and that's a great opportunity to show our software. Actually, I have many more cases on Crosstalk. Or VS, it was another topic at this DesignCon, and we, with my co-author Alex Manukovsky, invented new way to design VS on the base of this kind of localization properties and with formal localization metrics. Yeah, that's an interesting subject to talk about. And,
okay, so if people are interested, they can leave comments if they would like to see more videos, more visualization, how signals are traveling. Leave comments, and we can create another video with Yuriy.
Okay, thank you, Robert, and have a good weekend, and thank you everyone watching.
Thank you, Yuriy.
Goodbye.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our Fedevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments, and see you next time. Bye.